All right, students, here's the sixth one on my list, and I just realized that it was on my list, but it is identical, well, almost identical, to the practice test. Here, I don't think they give us any numbers to work with, but on the practice test or the study guide there, where I gave some problems from an old exam, I must have given this one and actually put some numbers here for pressure. So I don't know how much more information this will actually be, but I told you I'd do six, so this was on that list, so I'll finish it up. Maybe there will be some insightfulness because I don't think there's a video for it, and maybe it would still be useful. But this is the cycle, and it's got a bunch of questions for it. But again, it's just the technique, and maybe I'll just show that same technique that I think you should make a set of tables. One set of tables for the state functions, the PV and the T, and another table for the energies in the cycle of it all here. And maybe, unless it gets too long-winded, I might do what I did on number 20, where I added entropy at the end, and I don't know if that would be useful or not. But I'm going to just go ahead and see how much this takes me. But here I says has 1 mole of a sample gas, and it's monoatomic. Okay, so keep in mind then CV equals 3 degrees of freedom. So CP would be 1 more R above that, which would make gamma as this ratio, and so that would be 5/3. Okay. The ideal gas is taken through a cycle as shown. So point A has a pressure, volume, temperature, PVT, respectively, in terms of R and T. So they want us to write it in terms of R and T. Find A, the total energy entering the system by heat per cycle. B, the total energy leaving the system per cycle. And C, the efficiency of the engine operating at this cycle, and explain how the efficiency compares to that of an engine operating in the Carnot cycle between these same two extremes. Okay, so I guess I don't really need a table for the pressure, volume, and temperature, because they directly are giving those to me. But maybe just for completeness, I'll put that in here, because then this would be the pressure initial and volume initial, and I will then call this then initial temperature. So we don't have any numbers to work with, but then clearly as we go to B, we can see that it must be the same volume, because this is isovolumetric, and it's 3 times the pressure. And if we remember that PV equals to nRT, if you're comparing A and B and you have the same volume, but this is 3 times the pressure, this must be 3 times the temperature. And then as we go from B to C, you can see that it's isobaric from B to C. And so we have a constant pressure. And then the volume, according to the graph, doubles. And so again, you can kind of see here that if we were looking at from B to C and we had the same pressure, but we doubled the volume, we have to double the temperature. And so if this was at 3T initial, this is now at 6T initial. And this over here was T initial. And then as we go from C down to D, the pressure drops by a factor of 3, although the volume remains the same. So again, under those conditions, we must drop by a factor of 3. And so this must be 2 times the initial temperature there. Yeah, and so again, maybe those are so obvious that you don't need those. Or we could do everything in terms of P's and V's and then at the end use the ideal gas law to get the temperature. So like I said, I'll do that more for the completeness of the problem, and said, you really should probably do those all the time. The more interesting one is the table on energy. So let me go A to B, B to C, C to D, and then finally the return of D to A. And we can even put net down here, because as you've heard me say a few times, and I'll say it again, when we perform this little chart, maybe delta S, let's see how far we get here. I'll add to my little chart. The state functions, when you do a whole path, must be 0. And so there's an increase in pressure, decrease in pressure. Not pressure, that too. But and if we made one of changes of pressure, this chart is not changes of pressure. But if we made a change in pressure, they'd be 0. Change in volumes would be 0. Change in temperatures would be 0. But the ones in this one, the change in internal energy and the change of entropy would all be 0. Okay. But that's not quite what I wanted to say. What I wanted to say is when you make this chart, the first thing I always do is fill in everything that's given. And nothing is given in terms of energy, so I'll skip over that one. Then I put in the zeros. And for the zeros, remember, there is a 0 in any process that is isothermic. And for this, we have, looks like 2 isovolumetrics, volumetrics, and 2 isobarics. So none of those are there. But the work is 0 for the isovolumetrics. So A to B and C to D would have 0 work. Now the Q would be 0 for anything that's adiabatic, and we don't have any adiabatics for this one. And the delta S's would also be 0 for anything adiabatic, and we don't have any of that either. Okay. Or at least technically reversible adiabatic. Okay. So, like I said, I like to do the zeros first. And for this one, there aren't a whole lot of zeros. Now, the next one I like to always do is this state function, which is NCV delta T, even if it's not a constant volume process. And so I'll say it again, we derived it for a constant volume, but then we argued it was path independent. So then we argued we could always use this formula. So this is the next column I like to fill out and say, okay, this is for the always works. And so I won't pay attention to whether A to B is, well, I guess A to B is isovolumetric, but I won't pay any attention to that. This will work. And then maybe it kind of seems like it because I have isovolumetric. But I'm going to also use it from B to C, which is isobaric. Okay. So in this process, they tell me I had 1 mole. And as we mentioned earlier, it's monoatomic. So the number of degrees of freedom is 3. So the molar specific heat at constant volume is 3 1/2 Rs. And if we come back to our chart here, the change in temperature would be 3T initial minus 1T initial. So this would be 2T initial. And then I guess the 1/2 and the 2 would cancel off, and we would be left with a 3RT initial. And so I'll put that right here, and I think I'll be kind of answering their question in terms of R and T, find, and then it asks for a bunch of things. Now, also keep in mind that, and I'll put it up here above it, that according to the first law of thermodynamics, conservation of energy, these 2 columns must add up to that one. So if this is 0, then this must be a 3TRI. And actually, these would be pretty easy to do for this case, because these we do know for the easy case of isovolumetric and isobaric. And so I guess in this case, you might actually say these are just as easy as these. And in fact, if we were doing this one, we would have said Q equals to NCV delta T because it's a constant volume. And notice that's the same formula. So notice we get the same number, not a surprise there. Okay. Maybe I will do the B to C next. And so I'll apply this to the B to C. So this is 1 mole, 3/2 R. And coming to my chart, a C minus a B is 3T initial. And 3. Actually, now that I'm doing this one, I think of the workshop I was helping you guys with this one. Maybe it was a little different one. Well, I'm going to keep going here. Anyways, 3 times 3 is 9, and so this is 9/2. Let me call it 4.5 RT1. Okay. So here is 4.5 RT initial. Not 1, T initial. Okay. Now if I applied this from C to D, so this would be 1, and then 3 1/2 R. And then if I take the temperature at D, which is 2, minus at C, that'd be a minus 4T initial. Did I do that right? C to D? Yeah, 2 minus a 6. Okay, and it looks like this. 2 would leave me with a -2, so it's a -6 RT initial. So -6 RT initial. And again, right here, if I have 2 of them, I know this third one, so this is a -6 RT initial. Okay. And again, this is the one that is isovolumetric. So like I said back here from A to B, C to D, I'd really use the same equation. So don't surprise me, they come out to be the same. All right, and so now if I apply this same formula from the D to the A, again it'll be a 1, it'll be a 3/2 R, and I take the temperature at A, which is T1, minus D, which is 2, and leaves me a minus T1. And then that's a minus, and it looks like I get a 1.5 RT1. Okay, so minus 1.5 RT initial. And of course, we completed a whole cycle, so this should be adding up to 0. So let's see, this right here is a -7.5, and this is a positive 7.5, and adds up to 0. Okay, good. It makes me feel like I did this one correctly. Okay, nice. Now, I should also probably point out that even though I think in general these are easy to do because it's a state function, for this case, all these other ones are actually pretty easy to do also. And so one thing good about this cycle is these are pretty easy to calculate here, because for the isobarometric one, this one, B to C, we could say the Q is NCP delta T. So if I apply this right here to the B to the C, this would be 1. And as we said, this would be then 5/2 R for CP. And then we would take the temperature at C minus B, so that would be 3 Ti. And I guess that's 15 over 2 RT1. Let me write that as 7.5 RTI. I, not 1. Okay, and so 7.5 RT initial would fit there. Now, this is the place where, again, if you have any two of these, you can get the third. So we must be subtracting off 3, so that the 7.5 minus the 3 makes the 4.5. But also, the isobarometric, the work was pretty easy, because remember, the work was the minus the integral of p dv. So since the pressure is a constant, we would just have something that looked like this. So for us, if we didn't realize that, we could have just said, well, what is the pressure from B to C? And that would be 3 times the initial. And the volume change, again, B to C, so it would be 2 minus a 1 would be 1 initial. And so this would be a negative 3 pi vi. Then, if we use the ideal gas law, which is the PV equals to nRT, and set n equal to 1, we can see P and V equals to n is 1, and then an RT. And so sure enough, it is that same number. And so good, give me kind of a second way to double check. Not only do these add up correctly, but they also, when I calculate them separately, so I could feel pretty confident about that, especially during an exam. Okay. And let me kind of do the same thing down here. I'll do the Q for the D to A, which is isobaric. So it would be this formula again. It would be the 1, and then it would be the 5/2 R, and then it would be the final temperature, so A, minus the D. And so A would be a minus Ti. And so here we have a negative, looks like 5/2. Let me write that as 2.5. So minus 2.5 RT initial, which means that this must be a plus RT initial. And again, you can get that from this formula right here. And it would be the area under the curve. So it would be 1 unit of V and 1 unit of P. And then with the going the other way, it'd be change the negative to a positive, and the n would be 1 when you go PV equals nRT. So good. That matches when I do this, and it matches when I add it up. So feeling comfortable about all of those. And then if you were to add them all together here, for example, this would be a negative 2 RTI, and be the net work, if you will. And then hopefully this comes out then to be a plus 2 RTI, because these two should add to 0. And let's see, this is a plus 10.5. And if I subtract off an 8.5, I'm left with a positive 2.5. Yep. And so that's looking real good here. Everything seems to match. Now, at this point, I just filled in this whole table without really kind of looking back at what the questions were asking. So let me come back here. Maybe I didn't need to do everything, but I think it'd probably be best for illustration purposes that I did everything in that column, and maybe even entropy in a second here. But it says, find the total energy entering the system by heat. Now I really haven't done that quite yet. This is just the total energy entering by heat. So that's the Q. But they've limited it to the entering. See, my net Q right here is both what enters and exits. So just the entering part is the positive ones. So really, to answer A, Q, what we might call Q hot, as they show in the picture, the energy would be entering right here from A to B, and it would be also be entering from B to C. And we see that in the chart. Those are each positives. And that's what this question is just asking, how much entered, not the net, not an individual, but the two together. So this would be really a 10.5 RT initial to answer A. Find the total energy entering the system by heat. And then B, the total energy leaving the system by heat. So that would be the negative stuff, the stuff that is coming out. And in the PV diagram, thermal energy, they call it number 3, comes out on C to D, and it also comes out on D to A. So both of these are coming out. And so if I put the two negatives together, this would be the 8.5 RTI. And maybe I should put the negative. They kind of imply that in the question, so I don't know if negative is important because the way they said it, how much comes out. So they're asking for what is the value of the negative number. And so you don't want to say it's the negative of that negative number. But either way, I wouldn't make a big deal on the words here. What is the total energy leaving? C, what is the efficiency of the engine operating on this cycle? So remember, the efficiency is how much work did you get out compared to how much heat did you put in. So it's not the net work, it's how much did you put in. It's the net work up here, but it's not the net heat down here. This is how much you put in. So coming down here, the absolute value of the total work done, so the net work is 2 RTI initial. But the heat coming out is what we did in A, the 10.5 RT initial, where the R and the T initial would cancel off, and I would now have 2 divided by 10.5, which is about a 19% efficiency. Okay. The efficiency of the engine operating. Explain how this efficiency compares to that of an engine operating at the Carnot cycle. All right, so now let's look at the efficiency if this involved not these kind of processes, but the two isotherms and the two adiabatics. So it looked more like this. But I think they want the high temperature to be 6 times the low temperature. And so you would have cold over hot. And so you'd have 1 minus. And so the low temperature is the initial, and the high temperature is 6 times the initial. So this is 1 minus 1/6, which is 5/6. What's 5/6 in the decimal? 5 divided by 6. 83%. Okay. So this is a highly inefficient cycle. You can see why we didn't do it much. It's not really a good way to build an engine. It's an easy way to understand how to build an engine. You warm it at a constant volume like I did, and just put it in the hot water and clamp it and let the volume warm up, and then you open the valve while it's in the hot water, and so you kind of easy to do those, but they're not very efficient. Okay, good. Well, I guess technically I'm done with the problem, but maybe I will. If anybody's still listening here, go ahead and maybe do this last little piece and do the change of entropy, because in the last problem we looked at the change in entropy of the adiabatic, which was 0, and we looked at the change of entropy for constant temperature, isotherm. These are the other two cases. So let's look at the change of entropy when you have a constant volume. And then what's nice about that is we can replace that with NCV dt over T. And so I'll say what happens when volume is held constant. And you get NCV, those pull in front of the integral, and then you get a natural log of final over initial. And then, of course, what do you get when you have pressure held constant? Here's where your Q would be NCP dt. But the math is nearly identical. The only difference is you are going to use ACP instead of ACV. And so now we really have our four formulas. Maybe I'll put the other ones on here, but for the adiabatic, we got 0, and for the isotherm, constant temperature one, what do we get? Must have been, oh yeah, must have been that the temperature we could factor out, and then when we integrate it, we just get a Q. So we get a Q over T. So we have these four options, and including when we had like the liquid in the coffee, instead of using molar specific heat, since we didn't have a gas, we went back to the specific heat, and so this worked out for the liquids. And so for the liquids or the solids, I probably would do this for the entropy, and then I would do this, this, or this for the cases of, constant temperature, adiabatic, constant pressure, constant volume. Okay, so let's apply these two for this case. And so coming over to here, I'll go the A to B. So what is the change in entropy of A to B? As we just said, constant volume would be this 1 mole. And I forget, this was monoatomic, right? And so constant so CV would be 3/2 R. And we would have a natural log of final over initial. And coming back to this page, we would have then a final of 3T initial over T initial, so that's a ratio of 3. And I guess we can write this a couple ways. We can write this as 1.4 R times natural log of 3. Or maybe I'll make a decimal completely out of it. And go 1.5 times R, 8.31, times a, whoops, wrong log, natural log of 3. And so this is about a 13.7. Let me do an extra decimal. And so that is a positive increase. And so in my chart here, I'm going to put 13.69, and these would be units of joule over Kelvin since I used R as 8.31. And if it'll be okay, I will do the other constant volume, which is the C to the D. And that way I'll just do the 3/2 R and natural log. Okay, so from the C to the D, this would be a 2 over a 6. Which is 1/3, which, hey, now that's interesting, because that's the same number with a negative. So the 2 volume oximetrics, hey, that's A to B, increase of 3, C to D, decrease of 3. Okay, and it'd be the same formula. Oh, okay. Because here's what's going through my mind is, I look at this, and this is 1.5R, and then this is the natural log, and it's 1 over 3. The reciprocal of that would be 3 to a negative 1, and then I do a log roll down to here. And so this is going to come out to be a negative, and all these numbers are the same up here. And I didn't recognize that the process would be exactly the same. The temperature changes would be different. Would be the same factor difference, and it's a log. So the increase in entropy and the decrease in entropy is exactly the same. And I think then we have that for the isobaric process. So let's look at the B to the C, which, as we said, would be NCP, natural log of final over initial. And so in this case would be 1 mole, and CP would be 5/2 R. And then we would have natural log, and this is where we'll have to go to C over B, which would be a factor of 2. And I'll get a decimal in a second, but this is kind of fun because then the last process, the D to the A, would also be a 1 and a CP, 5/2 R. And it should be a natural log of 1/2. And so we would go from a final temperature of Ti and an initial temperature of 2Ti. Yeah, so this is 1/2. Which again would come out to be exactly this same number, where the 5/2 R is what you get here, and then you have a natural log, but instead of me writing it as a 1/2, I'm going to write it with a 2 to the negative 1 and then do a log roll. And so that is a decrease in entropy. And that makes sense, the decrease, and then it's exactly the same values. And so let me just use my calculator to get a decimal here. 5 over 2 is 2.5, 8.31 for R, and then a natural log of 2. And so that's a 14.40. So this would be 14.40, and this would be a negative 14.40. And again, adding them all up would come to be 0. And like I said, I didn't notice that they would have to be in groups of 2 zeros to add to 0. But given, now that we look at it, that makes sense. But I was expecting all 4 of them to eventually add to 0, but not in pairs. Guess I wasn't thinking ahead. Anyways, if that helped anybody, hopefully it did. And then that's my 6th one, and best of luck studying. Take care.